All right. Hi, everyone. Good morning. I'm so glad to see that many of you have made it to my session because, this is the last day of the conference. This is one of the last sessions of the day. It's not the best spot to have, but yeah, so thank you so much for coming to my session. My name is Thomas. I am a program manager in the Azure Cosmos DB team, and today my session is all about data modeling and data partitioning on Azure Cosmos DB. The subtitle of my session is what every relational database user needs to know. So let's start with a quick show of hands. How many relational database users do we have in the room? Good. So you made it to the right session, because my goal over the next 45 minutes is to help you get a better understanding of what it means to model and partition data on Cosmos DB. As I usually do when I'm giving such presentations, instead of giving you a very dry introduction to those different concepts, I'm going to explore them in the context of a real-world example. Okay? And I will do my best to make sure that all of you folks who are usually working with relational databases, you understand what are the main differences between modeling data for Cosmos DB versus modeling data for a relational database. Let's start with the broad question. What is Cosmos DB? We have so many different ways to answer that question. We usually say that Cosmos DB is a globally distributed, multi-model, high-performance, always-on database. But for the purpose of my presentation, I'm going to introduce it as being Microsoft's NoSQL database on Azure. And by NoSQL, I mean that Cosmos DB is a database that is non-relational and horizontally scalable. So let's take a moment to actually explore and understand what that means. And let's start with horizontally scalable. So whenever you are working with Cosmos DB, you have to understand that unless you are working on a very trivial kind of use case with very low requirements in terms of storage and throughput, most likely your data will be stored in not only one physical server, but on a number of different physical servers. This is something that we abstract with our concept of container, but most of the time, when you are working with a Cosmos DB container, under the hood, you are dealing with a cluster of multiple physical servers. And this is how we scale horizontally, right? This is how we deliver unlimited storage capacity, because whenever you need more storage, we just add more servers to your cluster to accommodate that. This is also how we achieve unlimited throughput, because whenever you need more throughput than what your current cluster can achieve, we just add more servers, we add more compute to make sure that we can meet your throughput requirements. The second attribute I used to introduce Cosmos DB was non-relational. What is that? Well, you probably know, most of you, that when you are working with a relational database, you have ways to define relational constraints between the different entity types that you are storing in the database. This lets you do things like define foreign keys between your entities and also perform join operations across your data set. Non-relational databases like Cosmos DB, well, they don't implement such relational constraints. Why? Well, the short answer is, as I just mentioned, we are horizontally scalable. And your data will most likely sit on not just one, but multiple physical servers, tens, hundreds, maybe thousands, depending on your storage and throughput requirements. Now, I'm not saying that it would be technically impossible to enforce relational constraints across a cluster of servers, but obviously this would have a major impact on the performance of the database and also its availability. And because Cosmos DB runs on what we call a predictable performance model that is even guaranteed by our SLAs, we don't expose any way to define relational constraints. Now, Cosmos DB is a non-relational database. Is it still suitable for relational workloads? Well, obviously the answer is yes. Otherwise, this would be my last slide, and I could let you go. And thankfully it is, because when you think about it, most of the real-world, real-life use cases we are dealing with are always more or less relational, right? But because Cosmos DB doesn't let you define relational constraints, we have to use different methods, different practices to actually materialize the relationships between your different entity types. And the key thing to understand here is that this approach is probably very, very different to what you usually do when you are modeling data on a relational database. All those best practices, all those intuitions that you have built over the past decades when using things like SQL Server, MySQL, Postgres, those best practices, they don't translate very well to the non-relational world, and many times there are also some kind of anti-patterns, okay? But fear not, I'm here with you today to introduce you to the right way to model data on a NoSQL database. So as I said, most of the time, I like to just explore those concepts in the light of a real-world example. And the use case I've chosen to cover with you today is the use case of an e-commerce workload. So this is, I would say, a simplified relational diagram for a typical e-commerce workload. What we see here is that we have customers, obviously. Each customer can have multiple addresses. This is a one-to-many relationship. And each customer can also have one and only one password that is here stored in a different entity. Besides customers, we also have products. Each product belongs to just one category. That's another one-to-many relationship. And we also have product tags. So each product can be tagged with multiple tags. This is a many-to-many relationship, right? Each product can have multiple tags. Each tag can refer to multiple products. And lastly, we have sales orders. These entities, they materialize a purchase. Every time a customer does a purchase, what we do is that we create a sales order, and we attach to that sales order details. And those details basically are the copies of the products at the time of the purchase. So what about we would implement that on Cosmos DB today, right? And let's start with the customers. So because Cosmos DB is a document database, where basically the data you are going to store are JSON documents, the first step we are going to do here is to translate those different entity types into JSON documents. We are just going to look at all the properties that these entity types define, and for each of them, we will create a corresponding JSON document. So we have one document for the customer, one for the customer address, and one for the customer password. So what you can note here is that if I just do that, I am keeping the references between those three entity types, right? Because addresses and passwords have a customer ID, I keep that references between those different entities. But because we are just storing JSON, and we can store any kind of JSON, any shape of JSON, another way of materializing our customer would be to put everything in just one document, right? What if we started with all the data that defines the customer, and to that original document, we would just add a JSON array containing the addresses, and then another sub-object to materialize the password data. So those are two different ways to materialize that. Either we can embed everything in the same document, or we can keep those different entities separated in different documents. Who thinks we should go with the first option, which is embedding? Okay. Who thinks we should reference and keep those things separated? Interesting, we have a divided audience today. So the rules to follow when you have to decide between embedding and referencing, they are pretty simple to understand. Embedding works best when you have a one-to-one or a one-to-few relationship between your different entities. That's our case here, right? We have a one-to-one relationship between the customer and the password. We have a one-to-few relationship between the customer and the addresses. There is an upper bound to how many addresses we will let the customer define in the e-commerce platform, right? So it makes sense to make everything sit together, even more because when we are going to fetch a customer, most probably we will want to fetch everything, not only the customer, but also the addresses, maybe even the password. So by putting everything in just one document, we would just have to read that one document and get all at once all the data that is related to the customer. The opposite, referencing, works best if you have to materialize a one-to-many relationship, and especially if that many is unbounded. If we would let our customers define as many addresses as they want, thousands, tens of thousands, this would bloat our JSON document, right? A many-to-many relationship obviously can only be materialized through referencing. This is not something that you can embed. And referencing works best when those different related items are either queried or updated independently. If our requirement would be to just fetch one address and one address only, maybe we should stick with referencing, but that's not our case here. For our use case and in order to materialize our customers, what makes sense is to embed everything in the same JSON document. So that's our first entity. We are making good progress on our modeling exercise. Now that we have defined our first entity, where are we going to store that thing? Well, we are going to store this entity in a Cosmos DB container. We are going to name that thing customers, no surprise here. But as you can see, I have a little question mark here, PK. This means partition key. Those of you who have already worked with Cosmos DB, you may know that whenever you are creating a Cosmos DB container, you have to define the partition key of that container. So what is the partition key? Well, that's the right time right now to dive into partitioning and to make sure that all of you really understand what is partitioning on Cosmos DB. As I already mentioned, whenever you are interacting with a Cosmos DB container, this is basically an abstraction on top of a cluster of different physical servers. What that means is that every time you are writing documents to a Cosmos DB container, those documents are dispatched and written to different physical servers. Now the question is, how do we decide that this document should be written to this server and that document should be written to that server? Well, technically, we don't directly associate documents with physical servers. What we do is that we write your documents into virtual buckets of data, and those buckets are called logical partitions. And it's those logical partitions that happen to sit on different physical servers. So for the exercise of data modeling, usually I recommend to just forget about physical servers, because this is our own implementation. But you have to understand whenever you are writing documents, those documents end up in different logical partitions. The question remains the same. How do we decide that this document should go into this logical partition and that document into that logical partition? This is where the partition key comes into play. When you are creating a Cosmos DB container, you have to define the partition key of that container. This is the name of the property we are going to look up in your JSON documents in order to understand to which logical partition it belongs to. Okay? So if we took the example of a container partitioned by username, as is the case here on this screenshot, we would end up with different logical partitions, one containing all the documents where username equals Andrew, a second one with all the documents where username equals Deborah, and so on. There are two main constraints to keep in mind when you are modeling data on Cosmos DB. First, we have an upper limit on the size of each JSON document. That limit right now is 2 megabytes. It's impossible to store a document that is bigger than 2 megabytes in Cosmos DB. The second limit is on the size of the logical partition. That limit is 10 gigabytes, meaning that I cannot have more than 10 gigabytes of documents where username equals Andrew. What I want to achieve when I'm defining my partitioning strategy is to achieve more or less even distribution of storage and throughput across my different logical partitions. I don't want to end up with a design where most of my documents are written to just one logical partition, and the other partitions just contain 2 or 3 documents. This is what we would call a hot partition. This is something we want to avoid. What we look for is a design where your documents are more or less evenly spread across the logical partitions. And same goes for the throughput. We don't want a design where most of your requests will hit just one logical partition, because again, this would be an obvious performance bottleneck and another kind of hot partition. What we want is that your requests are, again, more or less evenly distributed across your different partitions. Now, the choice of the partition key is super important when it comes to the overall performance and scalability of your data model. Let's take again the example of a container that we have partitioned by username. And let's imagine that we would issue that particular SQL query, select star from C, where the username equals Mark. As you can see, this query filters on username, which is our partition key. That means that all the results for that query, they sit in just one logical partition, right? Which is the one where username equals Mark. And Cosmos DB understands that. Cosmos DB understands that this is what we call a single partition query. So what we do, we route that query to the only logical partition that is containing the results. And as you probably understand, what that means is that this query will hit one and only one physical server. So the performance of this query will always be more or less the same, no matter how much data you have in your container. By issuing what we call a single partition query like this, what you essentially do, you decorrelate performance from data size. Now, what happens if I don't filter on the partition key? If I were to filter just on the favorite color, for example. So we have absolutely no clue. We cannot guess where the results for that query sit. So the best thing we can do here is to fan out that query to each and every logical partition that are underlying your container. And as you understand, this is a query that is going to hit each and every physical server that are under the hood. A cross-partition query works. I mean, there is, technically we support that fan out, but you have to keep in mind that it has an obvious impact on the latency of your query. This query is going to take a bit more time than a single partition query, but also on the number of request units that this query is going to consume. Those of you who are not familiar with request units, this is our performance currency. Okay? Every time you issue an operation against Cosmos DB, it has a cost, it has a hardware cost, and we have abstracted the cost that is related to CPU, memory, and I/O with that performance currency that is called request units. So any operation has a cost in request units, and what we try to achieve when we are modeling data on Cosmos DB is to end up with a design where your most critical operations are cheap in terms of request units. Okay? And that will not be the case for a cross-partition query. So now that we are strong of all that knowledge about partitioning, let's go back to our example and let's see how we can find the best partition key for our customers. There is no way to guess the best partition key just looking at the data. This is something that you can find out looking at the operations. Which are the requests, the most important requests that we are going to issue against the customers? For our example, I've just defined 2 of them. We should be able, obviously, to create a customer and also retrieve a customer. So when I log back into my e-commerce website, I click on my profile, I should be able to see my user profile. So we should be able to retrieve a customer by its ID. And because basically that operation is only going to filter on the ID of the customer, ID is probably a good candidate for the partition key here. What's going to happen if we choose the ID as the partition key? We will end up with as many logical partitions as documents in our database. And each logical partition will only contain 1 document because there is a one-to-one between the ID and the partition key. And that's fine, okay? Some people sometimes are scared in choosing a partition key that has a very high cardinality and a very high spectrum of potential values. This is actually fine. If I have millions of customers here, I'm going to end up with millions of logical partitions. There is no problem with that. It doesn't mean that I will have millions of underlying physical servers. These are 2 very different things, okay? It's actually a good thing to choose a partition key that has a high cardinality. So in our case, if I have now my customers container that is partitioned by ID, and if I just wanted to retrieve a customer by ID, what does it look like? So here I'm going to the Azure portal, and I'm going to use our brand new notebook experience. I don't know if some of you have already tried our integrated notebook experience. You should. So this is great. Now, when you are creating a Cosmos DB account, you can opt in to have an integrated Jupyter notebook experience to have a very easy way to explore and visualize your data. It's all Python, but don't worry, it's pretty easy to read. In order to just fetch 1 document, 1 customer by its ID, I'm going to call that a method called readItem. This is what we call the point read. I just give the ID and the partition key value to Cosmos DB, and when I get back is the corresponding document. Because I have partitioned my container by ID, ID and partition key value are the same things. So I just pass these 2 values to my method, and what I get back is my customer, Mr. Book, in that example, with one of the customers of my e-commerce platform. What is the cost in terms of request units of that operation? This is going to be very cheap. This only costed 1 RU. Okay? This is basically our baseline benchmark. If you just do a point read on 1 document that is less than 1 kilobyte, this is going to cost 1 RU and 1 RU only. Let's switch to our next entity. That is the product categories. Going to follow the exact same process. I look at the properties I have to materialize. I put them in a JSON document. Here is just 2 of them, ID and name. I'm going to put that document into a new container, product categories. How do I choose the partition key? Well, once again, I'm going to look at the most essential operations I need to perform against the categories. I should obviously be able to create or edit a category, but most importantly, I should be able to list all the categories available on my e-commerce website. So the SQL query corresponding to that operation would be just select star from C, which means list me everything that is available in that container. And for that specific query to be a single partition query, what I would need is that all my categories should sit in the same logical partition, right? Because if I ensure that, I'm sure that this query will always just hit 1 logical partition. The little trick I'm going to use to make sure that this is the case, I'm going to add an additional property to my categories, a category called type, and all my categories will have the same value for the type. So it's going to be a constant field. That's going to be category in my case. And I'm going to use that type as the partition key for my product categories. This may look a bit weird to you. No worries. This is just an intermediate version. We are going to iterate and finally optimize that model. So now how do I query my different categories? Going back to the portal. I can do that by just doing a select star from C, where the type equals category, against my product categories container. If I execute that, I get all the categories that have been stored in my database. As you can see, every time you store a document in Cosmos DB, we add some system properties. And sometimes you just don't need to see them. So what you can do in our example, if you just want the ID and the name, I could rewrite my query by just projecting the name and the ID of the category. And doing that, I will only get the corresponding results. Okay? What's the cost of that query? Well, it's going to be more expensive than a point read, obviously, because in order to execute a SQL query, there is more work that has to be done on the back end. It's going to be a bit more expensive. This is 3.6 RUs. Usually, the base cost for a SQL query is around 3 RUs or more. I'm going to very quickly go over the tags because the tags is the very same story as the categories. I start by putting my properties in a JSON document. I will store that document in a new container, product tags, and looking at the different access patterns I need to fulfill with the tags is the very same as the categories, creating, editing, and listing all of them. So I'm going to use the exact same approach. I'm going to add another property to my tags, type tag. I'm going to use that property as my partition key to make sure that all my tags sit in the same partition. And by the way, something that I haven't mentioned, could it be problematic to have all my categories or all my tags in one logical partition? Certainly not, because remember the upper limit for logical partition is 10 gigabytes. 10 gigabytes of categories. Looking at what we have to store in a category or a tag, just an ID and a name, this is going to be a very small JSON document, smaller than 1 kilobyte, meaning that I could store millions of different categories, which is probably good enough for my e-commerce platform. So I'm using the exact same approach here, using the type as the partition key for my tags. Let's move to the products. This is going to be a bit more interesting. Same approach. I create first my JSON document with all my product attributes, but here we have to remember that we have the tags, right? We have that many-to-many relationship between the product and the tags. The way I'm going to materialize that is by adding an array of tag IDs inside my products. Basically, I would have two different ways to materialize that relationship. Either I store tag IDs in the product, or I store product IDs in the tags. Okay, but there is one of those two sides where I need to materialize the relationship. Why does it make sense to put it here? Well, I will have much less tags per product than products per tags, right? In our case, that's another good candidate for embedding because my relationship between one product and its tags, it's one to few, right? I will have what, 10, 15, 20 tags per product? That's probably the high limit. So it makes sense to just materialize that by taking all the tag IDs with the product. Once again, I'm going to put that JSON document into a new container, products. Let's look at the access patterns to decide on the partition key. I should obviously be able to create and edit a product, but the interesting query here is listing all the products from a category. That's typically how my customers are going to browse the website. They click on the category, and then we list all the products corresponding to that category. And obviously, in order to be user-friendly, when I return a product, the customer is expected to see the full name of the category and the full name of all the corresponding tags. The SQL query here to get all the products for a category would be select star from C, where the category ID equals, well, the category ID I'm looking for. So in order, again, for that query to be a single partition query, what I need is that all the products related to the same category should sit in the same logical partition. So what would be a good partition key here? Category ID. That's an easy one. And usually, it's not that difficult to choose on the partition key. You just look on which properties we are filtering. When you are dealing with multiple queries, you have to see which properties we are commonly filtering on. But in our case, it's a pretty simple process. We are filtering on the category ID. This is going to be my partition key. So doing that, I can now, let me check. Yeah, sorry. I have a little issue here because remember my requirement in terms of what I need to display to my customers. Every time I return a product, I should also return the name of its category, the name of its tags. If I wouldn't do anything else here, what I would return is just a product containing a category ID and an array of tag IDs. So what I'm missing here is the name of the category and the name of the tags. So what that means is that in order to list all the products for a category, that first request is not enough, right? Because we are missing the name of the category, the name of the tags. In order to really fulfill my business requirement, I would need to issue a second query against the categories to fetch the name of the category I'm looking for. And then for each result, for each product returned by the first query, I would have to issue an additional query against the tags container to get actually the details of the tags. And this would let me correctly populate all the results I have to display on my front end. So this is going to work. I mean, obviously, doing that, I would be able to, from a functional point of view, this is going to work. Doesn't look very good. It's probably not very scalable either. And that's the moment where everybody in the audience who usually work with relational database are going to scream, where are my joins? Who moved my joins? This is typically a situation where I need to do a join operation across products, categories, and tags. But remember what I said. This is something that today you cannot do on Cosmos DB. You cannot do joins across multiple containers. So in order to work around that limitation, what we are going to do here is to introduce a level of denormalization. Okay? So whenever you are working with non-relational databases, usually you optimize your data models to make sure that all the data you need to return is ready to be served. Okay? In our example, whenever I return a product, I also need to return the category name. I also need to return the names of the tags. So I'm going to make sure that this is ready to be read whenever I'm querying my database. So in order to do that, I'm going to slightly augment my product document. I'm going to add the category name directly in the product. So basically, I'm going to copy the name of the category directly within the product, and same goes for the tags. Instead of just storing an array of tag IDs, I'm going to store the complete details of the tags, so I can also get the names. So every time I'm going to create a product in the database, I'm also going to inject those different pieces of data to make sure that I have everything I need in the database. Doing that, then, switching back to my Azure portal, I can now fetch all the products for a specific category. So here, this is the category ID for my electronics category, and I just returned the top 5 because I don't want to overwhelm you with results, but when I do that now, I get my products, and in each product, I have indeed the category name, and for each tag, I have the ID and the name. So in just one query, I get all the data I need to push to the front end and to display to the users. And this is going to work well until I rename a category. If I don't do anything else, as soon as I rename a category, I will fall in some inconsistency, right? Because I will get an inconsistency between the category and the related product, because if I don't do anything else, the products will still carry the old value of the category name. So what I need to do in order to solve that, looking at our current design where we have categories, tags, and products, every time I update either a category or a tag, what I need to do, I need to propagate that rename to the products, to the corresponding products. When I rename a category, that new name should be propagated to all the products from that category. Turns out we have exactly the right feature to implement that on Cosmos DB. That feature is called the change feed. So every Cosmos DB container exposes a change feed API. And this is an API you can subscribe to in order to get notified every time something happens in your container. So every time a document is either added or updated in a container, that document becomes published on the change feed API, and any piece of code was subscribed to the change feed receive the document to do whatever you want to do. So in our case, we are going to subscribe to the change feed of the categories. So every time there is an update of category, we are going to trigger an Azure function that will receive the new category and then propagate the new name to the products. And obviously, we are going to do the exact same thing for the tags. Let's see that in action. So what I'm going to do first, I'm going to do a point read to just retrieve one product from the category health. So here I get my product. The name is licensed soft salad, so it's a bit random. But what we can see here is that it belongs to category health. Next, I'm going to retrieve the health category by doing another point read. So this is the category coming back. I'm going to change the name from health to health and fitness, and then I'm going to do a replace IM. Basically, I'm just updating my category with a new name. So I'm going to execute that. And here is my new category. This is basically the payload that my Azure function will receive. And when I receive that payload, I know that, oh, the category with that ID has a new name. It's now called health and fitness. So I'm going to propagate that new name to all the products belonging to that category. By now, it should be already done. So if I fetch the same product again, you can see that it's still my licensed soft salad, but now the category name is health and fitness. So by just hooking a couple of Azure functions to the change feed of my containers, I have implemented a way to actually get consistency across my different containers. So whenever I rename a category, I don't have to remember from my application point of view that I have also to rename all those different products. This is something that is being handled automatically in a systematic manner under the hood by those Azure functions. How am I on time? OK, pretty good. Next, sales orders. That's the last entity we have to take care of. You know the drill. I'm going to start with 2 different JSON documents, one for the sales order, one for the sales order details. Is there any way to optimize that? we can embed, right? Because this is yet another one-to-few relationship. It makes sense to put everything in the same document. We materialize the details with a details array within the JSON payload. Why does it make sense? Not only because it's a one-to-few relationship, but also when I read a sales order, certainly I want to get everything related to the sales order. I want all the details, all the products that have been sold. That new JSON document, I could store it in a new container called sales orders. Choosing the partition key, again, can only be done when we look at the actual operations that we need to issue against the sales orders. Obviously, we need to create one. The second one is more important. So let's focus a bit on the second one. Listing all the sales order for one customer. This is typically an operation that any customer wants to do. You go to your profile, you want to see your recent purchases. This is an operation that can be done with the following SQL query, select star from C, where the customer ID equals customer A. And as you probably understand, for that thing to be a single partition query, I need all the sales order related to the same customer to sit in the same logical partition. So again, here, the right choice of partition key would be actually the field we are filtering on, which is customer ID. By partitioning my container by customer ID, I make sure that it's very efficient to retrieve all the sales orders for one customer. Now, before we go ahead, let's take a step back, and let's look at the different containers that we have created so far. We have created another container before, customers, containing our customers, and we partitioned that thing by ID. Now, if you think about it, that other container, customers, is also partitioned by customer ID, right? Because ID of the customer is the customer ID. So here we have two containers that are going to be partitioned on the same dimension. So would it make sense to put customers and sales orders into the same container? Is this going to hurt your brain? So mixing entities into the same container, first clarify that this is something that is technically possible because we leverage the schema-agnostic nature of a document database like Cosmos DB. You don't have to define any kind of schema, and you can write any shape of JSON that you want. We will just happily ingest it and index everything. So not only is it technically possible, but it is a best practice. It is one good way to optimize your model by putting together different entity types into the same container. Good typical reasons to do that. Well, it's suitable when your different entity types share the same access patterns. Maybe every time or many times when I'm fetching a customer, I also want to fetch the corresponding sales orders. And it's also suitable, like it's in our case, when those different entity types share the same partition key. So what I'm going to do, instead of having separate containers for customers and sales orders, I'm going to put both of them in my original customers container. Doing that, I need to slightly adjust the partition key of my customers container. I will change it from ID to customer ID, and that's a field I'm going to add in my original customers definition, because the partition key is a property that I expect to find in all the documents I'm going to write into that container, right? In the case of the customer, ID and customer ID are going to hold the same value, but that's fine. That's actually how we implement those patterns. I'm going to add another additional field, that's type. I will have type equals sales order for sales orders, type equal customer for customers. The reason why I'm adding that additional property, it gives me a way to distinguish between those two entity types. And when I query my container, I will be able to get one or the other. So just to clarify, doing that, I will end up with a container where each logical partition will contain one customer and all the sales order related to that customer, okay? And so now, in order to fetch all the sales order for one customer, the SQL query becomes select star from C, where the customer ID equals my customer, and also filtering on the type to get the sales orders. And this is something that I'm going to execute against the customers container. So let's do that. So this is the exact same query I just mentioned. Select star from C, where the customer ID is my customer, and the type equals sales order. Executing that, I get all the sales order for that particular customer ID. Okay? And that one did actually a lot of purchases. One interesting thing here is that by doing that, by mixing customers and sales orders into the same container, we kind of got our joints back. So if I had the requirement to issue just one query to get the customer and the corresponding sales orders, this is not something that I can write with just one query. If I issue the query here that only filters on the customer ID, this is going to return everything related to the customer, right? So both the customer itself and the sales orders. And now to make sure that my first result is the customer, the little trick is that I can order by type. And because customer starts with a C and sales order starts with an S, doing that, now I'm guaranteeing that my first result will be my customer, Mr. Book, and then the next one will be the sales orders related to the customer. So you see, we eventually got some of our joint capabilities back just by mixing different entities into the same container. I'm going to scroll down here. You really purchased a lot of stuff. And now to finish, still on our sales order, we have a last important operation we need to be able to manage. That last operation is listing all our customers by descending number of sales orders. So this is typically a back office operation, right? This is something I want to run from my admin panel. I just want to see what are my top customers. So who are the customers who have purchased the most on my e-commerce platform. In order to run such query, what I would need to do is that for each customer, I should count how many sales orders he or she has created, and then I should sort those counts by descending order, and then return the corresponding customers. This is something that today you cannot express in the SQL dialect that is exposed by Cosmos DB. There is no way today to write just one query. I mean, based on the data model we have now, there is no way to write a SQL query that would actually directly return that. The way we are going to, again, work around that limitation is to use our friend, the de-normalization. Okay? What I'm going to do is to add yet another property in my customers. I'm going to materialize the count of sales orders directly in that document. And then I will be able to do a sort on that particular property in order to get the results I want. So what I want to achieve, back to our customers container, is that every time I'm adding a new sales order, I also want at the same time to update the customer to increment my sales order count. Okay? The thing we can use, the Cosmos DB feature we can use in order to do that particular operation is to leverage our stored procedures. In Cosmos DB, stored procedures are written in JavaScript, and we execute them on the back end. And one interesting thing about stored procedures is that their scope of execution is one logical partition. So one stored procedure can update everything that's contained in one logical partition, and it's going to do that update transactionally, which is very important for us here. So in my case, instead of just creating a new document when I'm adding a new sales order, I'm going to pass that document to my stored procedure. So I'm taking the new order as a parameter. What the stored procedure is going to do first is going to read the customer. Then it's going to increment the sales order count, that new property that we have added. It's going to replace the customer. So this is updating the customer. And finally, it's going to do a create document to actually create the order in the sales order in the same logical partition. And remember that stored procedures are executed atomically. Those are atomic transactions. So only two options possible. Either my JavaScript function will succeed, and both writes will be committed, or my JavaScript function fails for some reason, and then any of those writes will be rolled back. So I'm guaranteed that I will have strong consistency between the actual count of sales orders and that new field I have added in my customers. So now the query to perform that operation becomes select star from C, where the type equals customer, ordered by that new property that we have added, descending order. So let's do that again on my notebook. This is the exact same query I just mentioned. I'm just doing a top 10 because I want to I have, I don't know, thousands of customers in my database. And in order to make it more readable, I just projected the ID and the sales order count. And so let's execute that thing. And here we get the ID of my top buying customers with their corresponding sales order count. Let's have a quick look at the request charge for that thing. Remember that before we were running a single partition query, and that thing returned in just 3.5 RUs, something like that. Here, that query was a little bit more expensive. Does anybody know why? Because this was a cross-partition query, right? Looking back at the query itself, it's filtering on type. It's ordering by sales order count, but the partition key is customer ID. We didn't filter on customer ID, so this is typically a cross-partition query. And as expected, that thing was more expensive than a single partition query because maybe it eventually hit multiple physical servers. But this is typically a situation where it's fine, right? Cross-partition queries are not evil. I mean, and I've never seen a real-world example where all the queries are single partition. This is very difficult to achieve, and in that case, I would argue that would be over-engineering my data model. I'm fine with that query being maybe a bit slower and maybe a bit more expensive in terms of request units, because this is a back-office query. This is something I will execute once a day, once a week, to see which are my top-selling customers. So I don't really care if it's slower and more expensive. So also one lesson to learn here: don't try to end up with a design that will yield single partition queries everywhere. First, it's going to be a major headache if you have a real-world example, and also because this would be obvious over-engineering. Okay, don't try to over-optimize and just optimize the most important operations that you have to fulfill. Looking at our final design, so we ended up right now with 4 different containers. One containing customers and sales orders, one for the products, one for the tags, one for the categories. There is one final last little optimization we can do here. Does anyone have an intuition how we can further optimize the design? I'm sorry? Tags and categories, right? As we mentioned before, good candidates to merge different entity types into the same containers are containers that share the same partition key value. That's the case here. We have tags and categories that are both partitioned by type. So one way to further optimize that design is to actually put them together in the same container. So eventually, we would be able to materialize our little e-commerce relational data model with 3 Cosmos DB containers. Key takeaways. Always start your modeling exercise by identifying which are the most important operations that your data model needs to fulfill. Without that step, if you don't have an initial understanding of which are the most important operations that my model will have to fulfill, there is no way for you to take the best decisions, because that's the information that will guide your choices of should I embed, should I reference, should I put the entities in different containers or the same container? Should I collocate, etc.? Should I de-normalize? You can only properly answer those questions if you have a good overview or initial overview of which are the operations that you need to design for. Partitioning, obviously, is critical if you want to achieve the best performance, the best scalability. Make sure that you really understand what partitioning is and how it works. It's not that complicated, but once you have a grasp of what's partitioning under the hood, then make sure that you are correctly leveraging partitioning. There are different ways to materialize relationships between different entities in Cosmos DB. You can embed, like we embedded customer addresses in customers. You can de-normalize and pre-aggregate, just like we did with tags and products. We kind of pre-aggregated the tag names into the product, so it's ready to be served whenever I want to do something, when I want to query my products. You can also store related entities into the same container, just like we did between the customers and the sales orders. Cosmos DB exposes different methods for you to implement de-normalization. The change feed was one of them. It's a very popular one. And don't be scared of using the change feed. Sometimes people think, okay, that's another moving part within my overall architecture and data model. Actually, we give you ways to consume and process the change feed in a very reliable manner, especially if you're using either Azure Functions or our own change feed processing library. We give you guarantees that the change feed will be processed very reliably and mitigating the risk of eventually having inconsistencies in your data model. Another way that we explored in order to implement de-normalization was stored procedures, which is a very powerful way if you need to de-normalize data within the same logical partition, because stored procedure guarantees a strong consistency in all your updates. Going further, that first link is a link to a GitHub repository that is empty right now. I am in the process of writing a full implementation of everything that I just presented, and even much more, because those Ignite sessions are very short. We only have 45 minutes, so I had to limit very much the different operations that I wanted to share with you. But I'm working on a full implementation that will go much further and show you, for example, how you can search products by tags, which is obviously a very common thing that you expect to do on an e-commerce platform. This is one of the things that I will also cover in that implementation. I hope to be able to publish that in the coming weeks or months. What you can do in the meantime, just go to GitHub, you watch the repository, so you get notified whenever I'm able to publish the source code. The second link may also be of interest for you, aka.ms/practicalcosmosdb. This is a link to our documentation that presents another kind of use case. I mean, those of you who have seen my previous talks, I usually take the example of a blogging platform, a social media platform. So this is a link to the documentation that actually covers that use case with the same process of exploring which containers do we need, how do we model our data, and how do we partition our data in such a situation. AzureCosmosDB.com is obviously the way to go for all our official documentation, but we also have a side website called gotcosmos.com. This is where we put even more samples and workshops and additional content. That's all from me today, but thank you very much for your attention. I will stick around for as much time as needed to make sure I address all your questions. Thank you.